Hey, so you are done with 8 chapters of calculus. Congratulations. And the good news is that you are now a differentiation ninja and you are an integral Jedi. You know what there is to know about derivatives and integrals. The bad news is that we get to use derivatives and integrals in exciting new ways in Chapter 9. That's not bad news. Chapter 9 is an introduction to a topic called differential equations. You can take entire courses in differential equations, multiple courses in differential equations. It's a very broad field, useful in lots of areas of engineering and mathematical modeling. But we'll just get a basic introduction to it. So let's just start with saying what is a differential equation. And a differential equation is an equation with an unknown function and or its derivatives. Should say its derivative or derivatives. So just as an example or two, here's a differential equation. It says some unknown function, its derivative is equal to x plus 2. And when we solve a differential equation, we figure out what the unknown function is. And you might be able to figure out what function has a derivative of x plus 2. Another possible differential equation might be the derivative of the unknown function is equal to 2 times the function itself. This is often the case where the growth rate is proportional to the size. Some things grow faster as they get bigger, like populations or the money in your interest-bearing accounts, right? But, and they don't have to use the y prime notation. They could use the dy dx is equal to y times x plus 2. And again, the idea here is to say the derivative of some function is equal to the function itself times x plus 2. And if you solve this, you'd be figuring out what the function is. You can certainly have a second derivative as well. Say the second derivative of the unknown function is equal to 4 times the original function. Okay, so solving means finding the function. So your answer will look like y equals, and you'll have some function in terms of x, right? Some of these aren't too hard to solve. Maybe you have an intuitive idea already. The first one says some function's derivative is just x plus 2. You might have an idea that the function is 1/2 x squared plus 2x. So check that out, see if it works. Go back to the original differential equation and fill in any y's and y primes. In particular, you just say, in this case, what's y prime? And you say y prime is 2x plus 2. X plus 2. And you're like, yeah, filling in y prime makes this equation equal. The second one, where the derivative of the function is equal to 2 times the function, consider, and I don't expect you to be able to figure this one out necessarily on your own yet, We're just checking to see if I tell you the answer, if you can see that it's the answer. So consider y equals e to the 2x. Is that what you were thinking? Maybe, maybe not. Let's see if it solves the original differential equation, though. Does it actually work? So come back to the original differential equation. Anywhere you see a y, fill in e to the 2x. And anywhere you see a y prime, fill in, what is y prime? Let's figure that out. What is the derivative of e to the 2x? And it's 2e to the 2x. So anywhere you see a y prime, fill that in. So let's just plug in our answer to the original equation and see if it actually works. So filling in, so here's our check. We're checking our solution. Filling in y prime with the derivative of my y would give me 2e to the 2x, and that equals 2 times, hopefully equals 2 times y. You can see that, yeah, it does indeed check. This third one, where the derivative of the function is equal to the function times x plus 2, that one, I actually can't think of the answer off the top of my head, unlike the other two. I just made it up, and it probably has a solution. There probably is some function that works that way, but I don't know what it is. Let me skip ahead to the last one, though. It says the second derivative of the function is equal to 4 times the original function. For that one, let me again suggest a possible solution. Let's check out y equals sine of 2x. And let's check that one, see if it works. So if we were going to check it, we would need to plug it back into the original equation. So we need y double prime, and we need 4 times y. So what is y double prime? So y prime would be 2 cosine 2x, and y double prime would be negative 4 sine of 2x. Let's check that one and see if it works. Y double prime is negative 4 sine of 2x. And over here on this side, it's 4 times y. Y was sine of 2x. And notice this time I was close, but not quite. These two things are not equal to each other, right? There's a pesky negative sign in here that I needed to get rid of. So this check actually does not work, and this is not a solution to the original differential equation. I feel like we got pretty close, just that negative sign. But again, for the moment, we're not focusing on any technique for actually solving. We're just checking to see if someone tells you the answer, can you even figure out if the answer works, right? Can you plug it back into the equation and check it? So that's one of your tasks for the homework tonight, is just to say, here's a solution. Can you see if it really is a solution? Does it really work? And the other task is they're going to want you to recognize that we can tell a few things about the solution just by looking at the differential equation. So for instance, if the differential equation looks like this, if it looks like this, I don't know what function works that way, what function you can square it and multiply it by e to the x and have it be equal to its derivative. No idea. But I do know something about how that function behaves. Keep in mind that the derivative tells you how a function increases or decreases. And keep in mind, if y prime is greater than 0, then the function's increasing. And if y prime is less than 0, function's decreasing. So now you should be able to tell me something about this unknown function, even though we can't figure out what the function is. Because look at what the derivative is equal to. Y squared. Squaring something, positive. So this part of the function will always be positive. E to the x, positive. Always, right? E to the x never goes negative. So what we've got here is something positive multiplied by something else that's always positive. So I know that the product here is always positive. And it tells me that this function, whatever it is always increasing. That function always goes up as you move to the right. I don't know much else about the function, but I do know that its rate of change is positive everywhere. Kind of looks like a little face right there. Let's make this a happy little dude. Okay. So you should be able to analyze something about how the function works. So again, another one might look like I'm basically making up the same thing. Shoot. I should point out that y squared isn't always positive. It's possible that y squared could be 0. So maybe I should have said something like y squared plus 1. There. Now it's always positive, always positive. This one, on the other hand, is always positive unless x is 0. So this one we could say something like it's I could say y is increasing unless x equals 0. And y is not decreasing at that point. But if x is 0, in which case y is flat, right? If you plug 0 in for x, you get 0 times 1, you get 0 for the derivative. So at that particular point, the function has a horizontal tangent line, and it's neither increasing nor decreasing at that particular point. Everywhere else it's increasing. I don't know exactly what it looks like, but it must increase, be flat at 0, and then increase again. So that's one possible picture. Okay, so 9.1 is really just asking you to explore the idea of a differential equation without having any techniques to solve them yet. So very conceptual, very not computational. So they'll try to twist your brain around a little bit, but come back at them, think deeply, and then in 9.2 we'll actually start looking at some techniques to solve these things.